All right, so this is the very first in-class exercise. We have a couple methods we like to explore. We probably start with the two methods that we have introduced from last week. The first is DFS, and after that, we'll move on to BFS before we go on and introduce the UCS search and also the A-star search. So for DFS, as mentioned, two ways where you can do it. You can use recursion, or if you wish, you can draw a table and you can use the stack to actually do the exploration, right? Here, we just assume that we will use the recursion, right? The starting node is S, right? So this is your node. You have multiple choices, A, B, and C. Just like before, whenever you have a choice, there's no specific rules about type breaking. We just follow the natural order, which means that if it's a number, we use numerical order. Otherwise, in this case, it's alphabet. We follow alphabetical order. So the first node that we're going to expand will be node A. So we move to node A. And then you see that now we are at node E. And finally, we are at G1, right? And this is the termination of the search. Because if you go back to the problem statement, our requirement is not to finish the traversal of the whole graph. Our purpose is to find the first goal state, right? So the moment you reach it, you terminate the search, right? And of course, as a practice, if you wish, you can continue the traversal. For this particular graph, you should be able, starting from S, explore each and every node, no problem. But in this case, we'll terminate here. So the goal state that we reach is G1, and the sequence that's leading to it is SA, E, and G1. Okay, so this is number one, the first search, DFS. And then we'll do the second one. So this time, what we want to do is actually the BFS. So BFS, again, if you wish, you can try to generate the sequence by visual inspection, but the more preferred approach, of course, is by using a table. So you are very clear about the sequence, what happened in between. So as before, we have this DQ operation. We have the visit and in-queue operation. And finally, we have the queue with the orientation. Head is at the front, and then tail is actually at the back. The first node that we visit and process will be S. This part is the same. So we remove S and look at the S, we can go A, B, and C, right? So they are all visited and in queued. So they will go into the queue in sequence. And then we process the first node. A goes to E and G1. And at this point, right, you see that G1 has appeared in the in-queue list, right? And this is the visitation. So the search at this point will terminate, right? You can, as before, if you wish, you can complete the whole traversal. But for the purpose of this problem, we'll terminate here. So if we write down the sequence, the BFS sequence, it actually reaches G1. And the sequence that lead to it will be SAB, C, and then E and G1. Okay, so this is the second one. So this is just a warm up. Pretty much still the old content we have from last week. Right, so now we have the real new method that we have. This is the UCS. The construction of the table is slightly different. It's mostly different in the case about number one is the underlying data structure. Number two is when the visitation actually happened. So it looks similar to the BFS because we have a queue, underlying queue, although it's a priority queue. But what's also making it different is that the visitation happens not during the in-queue operation. The visitation actually happened when we try to dequeue the element. Okay. So this is the dequeue. All right, so for simplicity, we will use the whole space over here as the priority queue, right? So we're not going to repeatedly just write repeat the same information, right? We just probably just write the information here. Okay, so the first information still is the first node going in is the S. Okay, so now this is another difference. When we enqueue element in the UCS, we do not just enqueue the node label, because now we have the weight of the edges that we need to consider, right? So now we need really 3 pieces of information. And number 1 still is the node label. But number 2, this is the cost. The definition of the cost is the accumulated cost. If you start from the origin, in this case, it will be S, all the way, right, based on the search sequence that we generate, and to this particular node level. So S is the beginning, so your cost will simply be 0. And the third information is for later we want to do the path recovery, right? So we need to memorize for this particular node label, where are you coming from? This is the first node, right? So you're coming from nowhere. We just use this is representing none essentially, right? So you replace this, you dequeue this, you're going to remove this. So the node S comes out. So we can provide, for example, some tracking information just to indicate that where is the S coming from. So from S, we're going to enqueue A, B, and C. We're going to repeat the same process to provide some additional information. So we start with A, right? So when we compute the cost over here, it contains 2 components. The first component, because again, every time a node is being enqueued, it means that you are coming from somewhere. In this case, A, B, C, all of them are coming from S, right? So the first component is the cost it takes you to reach S, right? The node that you're coming from. And that cost is 0. The second part is the actual edge cost, right? So now you have reached S with the cost that's indicated as the first component. What is the edge cost that will bring you from this node, the previous node, to the current node? The edge cost in this case is 3, right? So that will be the second component, 3. And you are coming from S. This is your previous node, right? So we do it for A. We also do it for B. For B, the cost is calculated similarly. The first component is still 0. Second component will be S to B. The cost is actually 1. And you are coming from S. The third component is C. So it's going to be the same, 0 plus SC, which give you a cost of 5. And you are coming from S. So now your priority queue contains 3 components. When you extract the element from priority queue, you actually use the center element, center cost over here to rank all the individual items. So in this case, B has the lowest cost of 1, right? So the next node that will be extracted will be B. B is actually coming from S. Okay, you look at B, B will actually go to C and F, right? So at this time, you see that we have the second copy of the C appearing. This is allowed because at the moment of enqueuing, the node is not visited yet, right? And then one of the important property after we generate the second copy of the C is that because the priority queue have this property that you always only take out the nodes with the lower cost. So even in the case that you have duplicate copies of the same node, you always will extract the copy that has the lowest cost. And because after you dequeue, you visit that node, right? Which means that if you have any other ways of reaching C, the same node, but with the higher cost, they will have no chance of being visited and extracted, right? So I think this is a very important point, right? So during the whole UCS process, you may encounter multiple occurrences of the same node. It basically represents different ways you can actually go around the graph and reach that particular node. But based on the design of the algorithm, you will always pick the one path that has the lowest cost. And this is the reason why UCS is able to discover the shortest path for you. Because of all the alternatives that you can reach a particular node, you always pick the node, pick the path that have the lowest cost. Right? So we'll use C as an example. Later you will see how that happened. Right? The second example is C. C is actually coming from B, right? So you look at the costs that go to B, which is 1 over here, right? This cost over here. This is the first component for C. Second component is B to C, right? Which give you a cost of 2. And you see that the second component actually comes from B. Now you compare these two components, right? So the first component is 5, the second component is 3. So this one will be overwritten, right? So this one will take over the previous component due to the fact that it actually has the lower cost. And then F, yeah, we also need to insert that. The first component of the cost is 1. Second component will be BF. BF give you the cost of 2. Now, when we are about to extract the next node, you see that we have a 3-way tie. A, C, and F, they are of equal cost. All of them have the cost of 3. So again, you can break the tie any way that we want. But in this case, let's try to break the tie by using alphabetical order. So we pick A first. From A, you can go to E and G1, right? So in the previous method, this is when the search will terminate, right? But in this case, you see that we'll continue, right? Because this is not a visitation yet. So the cost of E is actually the previous cost, which is 3, plus AE, right? You look at AE, the cost is 7, and you are coming from A. And then we have G1. Very similarly, the previous cost is 3, but this AG1 is actually having a cost of 10, right? You're coming from A. So again, look at it, look at this list. We have S, A, C, B, C already visited. Sorry, C is not visited, C is being overwritten. The next in line will be C, right? So we'll visit C next. C coming from B. And for C, we can go to G3, right? So the quantification of cost is the same. The first component is 3. Second component is C, G3. The cost is actually 11. This is coming from C. Again, we pick the next node based on the cost. F will come up next. From F, we will go to, where is F? Oh, over here, go to D. And the cost calculation is the same. The previous cost, which is over here, right? Give us 3. And then the second component is FD, which gives us 1. So D is actually coming from F, right? So we are almost there, right? You look at the remaining list, you have E, G1, G3, D, cost is 10, 13, 14, and 4. So D will be chosen as the next one. D coming from F. D goes to G2. So now G2 goes in. The previous cost is 4 based on this one. And then D, G2 give you 5. We are coming from D. Okay, so this is it actually, right? So you look at the next options. G2 actually have the lowest cost, right? So it will be dequeued and visited. And at this point, we will terminate the search. Okay, so now the search is terminated. We actually have 2 different sequences we can extract. Number 1, which is being asked, is about the visitation sequence. Everything in the first column tell you about the visitation, right? So if you want the visitation sequence, it's going to be S, B, A, C, F, D, G2. But this is actually not the shortest path that will go to G2 from S, right? Because this simply means that when you just do the expansion from the starting point outwards, what are the points that you're going to encounter, right? So what we really need is actually a path. And now this is the reason why we need to memorize for each and every node where you are coming from, right? Because G2 now is the destination that we have identified. what we do will be backtracking. We write down G2 first, and we do backtrack, right? G2, you based on the previous node you have memorized, you actually come from D. And then you go to D entry, right? D come from F. So previous node is F. You go to F. F actually come from B. So you write a B here. B come from S. So I write it down here, right? So this is my shortest path. And finally, the cost of this path should be the final cost that's embedded in my entry inside the priority queue, which is 9. But as a final confirmation, right, because we have the shortest path, we can double confirm. We can calculate whether or not the cost from the graph indeed is 9. So we look at SB. SB's value is actually 1. BF is actually 2. FD give you 1. And then DG2 give you 5. So in total, if you sum up all the H costs accumulated, this shorter path cost is indeed 9. Right, so this part are exactly the same, right? What's really different is actually the consideration of the heuristic function, which is the value that's inside individual node, right? The G function part is exactly the same as before, the UCS component, right? So let's see how it goes. We still include the S. The calculation of the cost is exactly the same. Initially, the G function part is 0 because you start from the origin, but you have the second component, which is the H value. In this case, the H value is actually 8. And then the previous node is empty, right? So actually for S doesn't matter because it is the first node. You pick S. From S, you go to A, B, C, right? So we do it one by one, so we'll see the cost calculation. So for A, right? So remember there are two parts, the G function part and the H function part. These two parts need to be separated. The first part, when we do it, we still look at the previous cost. The previous cost, we only take the G function part. We use that to update the G value. So to reach S, the G give us 0. So the previous component, previous value is still 0. And to reach out, you have SA, you have 3. But this time, this is the G component, right? This time, we also need the H component, which is the value inside. In this case, it will be 9. And you are coming from S, right? So this is for node A. For node B, we do exactly the same thing, right? The previous G cost is actually 3. And then SB give you 1. This is G. But your H is actually also 1, right? You're coming from S. And then we have C as well, 0 plus SC, which is 5. This is G. And then the H, which is 3. So now the selection rule, exactly the same. We look at the center component, the combination of the G value and the H value. We pick the one that has the lowest cost, right? The second one, based on this criterion, will be B, have the combined cost of 2, right? So B will be chosen. It's coming from S. B will be going to C and F, right? So we have C and we have F, right? We look at C first. And the previous cost over here, right? So again, this part need to be very careful, right? When we calculate the G, we don't utilize the whole part. In other words, we don't use the whole cost, which is 2. We only use the first component, which is 1 over here. This is the G function part. So when we update the new G function, we only use the G function from the previous node, right? So it's going to be 1 plus BC, which is 2, right? So this is the G component part. The H component part stays the same. It's still the 3 value, the value of 3 for C. But this time we are coming from B, right? So you see that conclusion is the same. The earlier copy of the C will be overwritten. You will not appear. And then we have F, still 1. This is the B's value. And then we have BF, which is 2. And then the H value is actually 5. 5, right? Okay. And coming from B. So now you look at the the cost, right? C turned out to be having smallest value. This is 12, this is 6, this is 8, right? So C will be chosen the next. So we have C coming from B. C goes to G3. So we have G3. G3's cost, the very first component is the G function part, right? So we have 3 plus 11. This is the G function part. The H function part, on the other hand, is 0, right? So one of the requirements of the heuristic function is that when you reach the final destination, this is your goal state. And the H function actually estimates the estimated cost from the current location, the node that you are dealing with, all the way to the goal state. So in other words, if you are at the goal state, then you have to make sure that your heuristic function will always return 0, which is indeed 0 for all the 3 goal states in this case. You look at G1, G2, G3, their H that's inside the node is actually 0. All right, so G3 is actually coming from C. All right, so I think this is okay. So the next node that we're going to process will be F, having a cost of 8, right? So F is actually coming from B. F will go to D, right? So we write down D. These costs will be the first part, which is 3, plus the cost, the H cost, right? FD, which is 1. And then plus the heuristic cost, which is 4. And D is actually coming from F. So you review again, right? So D is actually having the smallest cost. So D will be removed. And then D will lead to G2, right? So we'll write G2. For G2, the cost will be 4 coming from here, right? Plus 5. The H function will be 0. And G2 is actually coming from D. And you look at all the remaining nodes, right? G2, as a result, will be processed the first. So now if you compare to the previous instance, for this very small graph, the saving is limited because you only have so little nodes, but still, I mean, the visit sequence is reduced by 1. So we have SB, C, F, D, G2, right? So it should be slightly faster if you run the A star for this graph. But although the visit sequence is different, the shortest path that we discovered should be exactly the same, with exactly the same shortest path cost. Sometimes it may occur that, okay, so you can have multiple paths at exactly the same cost. But in this case, the shortest path is unique. So we should discover exactly the same shortest path. So let's do a final check to make sure that it is indeed correct, right? So G2 is coming from D. D is coming from F. F is coming from B. And then B is actually coming from S. The cost is this G value that we recorded the last for the gold node is actually still 9. This part is still correct, right? So we do the final check, D, G2, this is 5, this is 1, this is 2, this is 1, right? So indeed, the shortest path is correct and with identical cost as the previous method in UCS. All right, so this is the A star algorithm, exactly the same process, but with the introduction of the heuristic function. Right, so any questions for the above 2 methods? Yep.
The value of the node is the shortest.
Yeah, very good. Good question. So we go back to the design of the A star. So the method itself is simple, but the key critical additional design test for the user is how to determine the H function. So H function need to be come up by individual user. There's no fixed rules as to how you can generate the H function. There's only one requirement though, is that when you generate the H function, you should never overestimate the cost. And the reason for this is that if you overestimate the cost, inside the priority queue, right? If you go to the priority queue over here, this H function value is an overestimation. You may make the real optimal node less attractive. And as a result, right, the search method potentially can miss that particular node. But if you underestimate, it's actually okay. It just take longer time for that node to be discovered, but I mean, you do no harm, right? But if you do overestimation, then you run the risk of missing the real optimal shortest path. Okay, so now how do we calculate the H value? If the problem is on the map, it's the physical routing, right? The easiest way to ensure that you provide some meaningful value, but at the same time, you guarantee that you will never overestimate is the straight line distance. Right? If you connect, I mean, whenever you are at a particular point, you just take the coordinate, right? And then you look at your destination. You have another coordinate. You just calculate the straight line distance, which is very simple, right? Just use a simple Euclidean formula, and you can calculate this. You can use that as the heuristic function. Very easy to calculate, but then it can help you to reduce the searching time enormously.